Okay, so guys, I'm just going to revise this energy before we start with work. We have done a little bit of the work in grade 10, but I just want to cover the energy because energy is part of the section as well. So you can use your energy formulae as well. So remember that you get your kinetic energy, which is a half mv squared. The faster the object is moving, or the bigger the mass, the bigger the kinetic energy. You have your gravitational potential energy. The higher the object is, the more potential energy. Oh my gosh, I see this massive glaring thing. You know, I've used these notes for like 4 years now, and that's the first time I've seen that. Okay, so EP is equal to mgh. So the bigger the mass, the bigger the gravitational acceleration. So if you're on a different planet, the bigger your potential energy will be. So it's all directly proportional. Okay, you get a conservation of energy. Now be careful. You've got you've got a law of conservation of energy. And you've got, oh, I don't know where it is now. I don't think I've put it on here. Okay, well, anyway, let's have a look at this. So you've got a conservation of energy. So energy is neither created nor destroyed. It simply changes from one form to another. Okay, so a light bulb is electrical energy to light and heat energy. That's why the concept of making electricity seems so trivial, because if you could just use any energy to convert to electrical, it should work. Even using things like sound energy, it should work. So there's a law of conservation of energy. This is the total amount of energy before and after energy transformation remains constant. Now that is any energy, okay? So here, this goes from electrical to light and heat, but the total energy before must be the total energy after. Even if you're not getting a lot, say the light bulb you're using is not very bright, okay? I'm not saying it's stupid. I mean, it's just not, it's quite dim, okay? And but it's getting extremely hot. So you wanted light from it, but it's getting so hot. So it doesn't mean, oh, well, I've lost energy. It just means it's being transferred into something else, okay? So, or energy has disappeared. Okay, it's not that. So that is the law of conservation of energy. Now, one thing I wanted to show you with this, because this is where this happens, is that this illustrates the conservation, and you'll remember this because we did this in a lot. Conservation of mechanical energy. All right. So this is where, can you remember? Mechanical energy is your kinetic energy would be equal to your potential energy. Kinetic energy at the top, bottom, would be equal to your potential energy at the top. Okay, so that's essentially, so this is, another thing what we can say is the kinetic energy initially plus the potential energy initially should be equal to the kinetic energy final plus the potential energy final. Okay, so that is another way of writing your conservation of mechanical energy. It's specific energy. Mechanical energy is potential and kinetic. Potential and kinetic. Okay, so remember the ball drop. This is kind of ironic, hey, what you're doing now in your prac. So, not ironic, it's appropriate. So at the top here, it's at its highest or maximum height. So that means you've got your maximum potential energy. Okay, and in its vertical state, there is no movement. So if you push it off there, there's only horizontal state. So in its vertical state, it has a zero velocity. So V is equal to 0, which means your kinetic energy is equal to 0, okay, at the top. When it reaches the bottom here, you know that anything that is free falling accelerates. And so it gets faster and faster and faster as it falls. And just as it hits the ground, your potential energy is now 0, but your kinetic energy is now maximum. So you can see how the energy transformed from potential into kinetic. Now remember, when it hits here, it's going to lose a bit of energy. You're probably going to find energy is going to be lost in heat because there's going to be a bit of friction with the ground. It's going to be lost in sound. And remember that sound energy carries on. You hear it in your ears. Your ears vibrate. It goes into this, then probably heats up a little bit in your body, and then your body loses heat. And it just carries on, carries on, carries on. Okay. Halfway through, we know that the potential energy is half what it was here, and the kinetic energy is half, and so they will equal each other. Your potential energy here would be greater than your kinetic energy. Your potential energy here, sorry, I see I made a mistake. Doesn't matter, I put K there first. Is then your kinetic energy is greater. Okay, I think you should remember this. And if you had to do this in terms of this, you'll see that your kinetic energy here would be 0, because at the bottom here, your height would be 0. So you can see where we get the kinetic energy initially, plus the potential energy, because that is your mechanical energy. So another way to say this is your mechanical energy initially is equal to your mechanical energy final, because it is conserved. All right, so your kinetic energy, now let's say we are initially 0, so that means that falls away. All right, your potential energy is 0. Let's just say you could work it out any way along there, but we are looking at the top and the bottom now. So at the bottom, you don't have potential energy because your height is 0. So if you did that and that, it's exactly like saying, well, your energy, potential energy at the top is equal to your kinetic energy at the bottom. And that's exactly what we said there. But this is the actual thing. So here you can see, here I've written it here. Potential kinetic, or you can say your mechanical energy initially is equal to your mechanical energy after, or final. And your mechanical energy is made up of your potential and kinetic. This is the conservation of mechanical energy. Be careful, it's so easy to get them mixed up. The law of conservation of energy versus the law of conservation of mechanical energy. Okay, so just bear that in mind. Now, another thing is that the law of conservation of energy is always there. But mechanical energy, the conservation of mechanical energies, it might not happen. Let's think what could happen. It could be there's air resistance that causes a problem. Let's say it drops and it hits branches of a tree. It's lost some energy, and so it's not going to hit the ground with the same amount of energy. So mechanical energy is not always guaranteed, especially in everyday life. But the conservation of energy is always guaranteed, because remember, if the ball hits the tree is going to move a bit, and so that energy just went somewhere else. Okay, so bear that in mind. Then remember, you got the pendulum, and a pendulum is going to be swinging. Okay, and in an ideal world, it won't stop swinging. You'll have perpetual motion where it doesn't stop. But we know there's resistance, air resistance. If you could do this with a frictionless cord in a vacuum, it would actually carry on forever. Okay, and remember, the same thing applies here. You can imagine this thing as it goes from there up, and it stops, and then comes back down, and stops, goes around, up. So it stops at the top here. So it means that the kinetic energy up here is 0. Okay, so always just think of that. The kinetic energy up here is 0. Here is where it's going its fastest. It has now reached the bottom. Doesn't matter about the direction it's taking. Remember, it only has the force acting down on it. And so it will accelerate with G as usual. So my potential energy now is 0 because it has reached the bottom of it. Now, also remember that the height of the pendulum doesn't matter about how high you are above the ground. It is to do with the height of the actual string. Okay, so this is the height from the top there to the bottom of the pendulum there. So if you had to look here, oh sorry, I lie. It's to do with this top. Sorry. Okay, and so there's my height there, and over here you have a 0 height. Okay, so, and my kinetic energy over here is the maximum, and my potential energy is the maximum. So it doesn't matter which side you're working with. They're both going to be the same. Remember, you're always going to assume there's no friction. It's in a perfect world, unless you are given something in a question that details something, that it's starting to slow down, or it's very humid, or there must be something in the question that tells you, wait a minute, I need to look at something else. Okay, so I would like you to do these think tanks. Did I say you were going to continue with them? Let me just see what I said. Okay, no, I do want you to just do that, because I haven't used too much time today. So if you could quickly do 4, 5, and 7, and 1, 4, 8, 12, and 13. Those were the ones that I identified as good examples to do. All right, let me know if you want to Google me to ask questions. I'm very happy to do that. Don't worry about data or anything. I do have Wi-Fi. Okay, so yeah, thank you very much and enjoy. I hope you understood.